Alright, welcome. In this video, I'm going to be giving you my top 5 tips for using Desmos on the AP Calculus exam. And my first, and probably the least surprising, is that we need to be able to do the fundamentals. They say on the College Board website that we need to be able to graph a function on an arbitrary viewing window, we need to be able to solve equations, and we need to be able to do derivatives and integrals on a calculator. So let me show you how all that would work. So if we were given a function like f of x equals x log of 2 plus sine x on a viewing window 0 to 7, well, we could just kind of go over here and graph that, type in f of x equals x log of 2 plus sine x, and then we can also give it a domain by using the curly braces. And you can find these in the keyboard down here, and you can also just type them in using your the keyboard on your computer. And I'd say the same thing about less than or equal to. You can type less than and then equal to, or grab it from the menu. If I want to solve the equation f of x equals 3, really what I want to do is see where this graph intersects with the line y equals 3. I've got that. Okay, I see that there's an intersection right here. I can hover my mouse over the intersection and it will show that to me. What I can also do is I can click on this little box right here, export point to expression list, and it'll tell me right here. Okay, so I'd say that's going to be x equals 5.934. If I was asked to compute the derivative of f at x equals 3, well, that'd be like f prime of 3, use the apostrophe, and that would give me negative 0.626. And if I wanted the integral, you can, all these things you can grab from the, keyboard down at the bottom if you're, using a tablet or something, but you could also type in int, and that'll give you an integral. I think that's probably fastest, most dependable, most easily remembered for us. And then that'll be just f of x dx, just like you would think. And so I get these values, I would copy them down onto my paper, and then I'd be happy. Now, one thing I do want to point out about integration on the calculator is that if I want to integrate, something like f of x plus 6, and I do that, it's going to throw an error. And I need to do an error at least once on this video. So I can show you that if it's going to have an error, you can hover your mouse over it and it will tell you what its problem is. Now this is saying it must end with an integration variable like dx, and you might be saying like, well, you've got a dx. Okay, and I'm just doing this to remind you that when we have addition or subtraction in our integrand, we need to be using parentheses. And we can get into more discussion about the deeper meaning of integration and the widths and the heights of the rectangles and stuff. But I think for the sake of this video, I'm just going to say remember to put parentheses around your integrand if it's got addition or subtraction, especially if you're getting that type of error. Now, the last example I've got for you related to this function and this graph is that if f is the derivative of g, where does the graph of g have inflection points? And so if you think about it, okay, we're looking for the sign changes in the second derivative, and we're looking at the graph of the first derivative, we're looking for the extrema. And wow, one thing you can do is graph y equals f prime of x. I kind of feel a little obligated to show you that. Okay, we can find the zeros there. Another option that we have is we can just go look for the extrema, hover our mouse, and export the point to the expression list. And so then we'd be looking, okay, these are the x values of the points of inflection on g because they're the extrema of its first derivative. And we could say, okay, x equals 2.624 and x equals 3 pi over 2. Now, when asked about an inflection point, we should always give a reason, and that reason is always going to be the same, the second derivative change sign. Okay, number 4, polar. Desmos is particularly helpful with polar, in my opinion, for a few reasons. Now, this is a BC only topic, so if you're a student in Calculus AB, you might just go ahead and skip on to, tip number 3. But if you are interested in graphing polar curves, this is really nice. So we're going to find the area of 3 petals of the rose curve r equals 2 sine of 5 theta. Okay, so I'm going to just type it in, just like you see it. Now, to get that theta, I will show you. You type in theta. Okay, but I think it's also a symbol you can find down there in the keyboard. Okay, so I get that. I see it's got 5 leaves, okay, or petals, and I'm going to say, okay, 3/5 of the area. But one major upgrade over the handheld graphing calculator is it tells you, hey, this is one of those weird ones that traces out its graph on only 0 to pi. So that might save me on the integration from making an error with the bounds. Now, you should remember that an area is going to be, the area of the full thing is 1/2 integral of r squared d theta. Okay, now we're going to integrate from 0 to pi because we can see that's the domain. But since it's only 3 petals of the curve, I'm going to multiply that by 3/5. If I just type it in just like I see it, I'm going to get myself an answer. So 1.885. Now, that's another thing I really like about Desmos as opposed to the handheld graphing calculator is the flexibility of notation. You just type it in just like you see it for almost everything. And I'll show you the kind of the one main exception here in a couple of minutes. Right, now, one thing to be aware of, though, when working with Polar and CalBC on the free response with the calculator, is that it does not do intersection. Okay, no calculator calculates polar intersections because it's just really not. It's not that simple. But you see, you hover the mouse over the intersection point, you're not getting anything. It's very frustrating. What we've got to do instead is graph these rectangularly. Because if all we change is the letters, okay, the graphs will look different. They're not graphed in a polar sense anymore. But the intersection point will give us the theta value of the intersection on the polar graph that we were seeing earlier. So if I hover over there, maybe I even, grab that to my expression list. And I'm going to copy that down, call it theta star or something. Now, I'm going to go back to the idea of the polar graph, but I'm going to leave these on because all I would have to do is say r equals f of theta. I said 0 to 1 pi, I think was the way to go on that. And then r equals g of theta on 0 to 2 gives you the best picture. I was kind of using red and blue for them. But what I'm saying is that, okay, we get the area sweeping out here until the intersection on blue, thinking about just rotating in the usual unit circle way, and then we're going to integrate against the red curve until pi over 2. Okay, so I've written down my expression, and I'm going to be typing it into the calculator. But if I've got this intersection and I want to just kind of use that as the bound of integration, what we could do is we could just like call this A, right? And just like letter A, or really any letter you like besides like R, F, G, T, theta, something like that we've already used. So what I'm going to do is I'm going to take 1/2 of the integral from 0 to A of theta squared. I can just call it t squared dt, or you could have called it f of t, right? We could have done that. Plus 0.5 of the integral from a up to pi over 2 on basically the blue curve, and that was g of t. Okay, but because it's polar area, I do 1/2 r squared d theta, and I get 0.541. That looks pretty reasonable based on the diagram that I'm looking at over here. About half a unit of area. All right, number 3, use the table feature. It's great for absolute extrema. Now, I recognize that the example I've got for you right here is a little overly simplistic. It's very unlikely to be asked in a calculator section because I'll show you what you can do. If we just say on the interval 0 to 8 and we apply that restriction, we can, whoops, maybe I didn't put less than or equal to 8. I don't know, I did, but I think if we zoomed in, we could figure out what, 8, negative 1.6, and we could see that the absolute minimum is down here at 7 and negative 6.7. But, the ones on calculator free response usually have a little bit more subtlety, involve an integral, something like that, but just for the sake of simplicity, I'm going to show you me typing in the word table. Okay, that works. You can also go up here and add the plus table that way if you like. But what I'm going to do is we're going to check the endpoints, 0 and 8, okay, and we're going to train this. Okay, we're going to need y instead of y to be h of x. Okay, and then instead of y1, we're going to say this is h of x1. Okay, and I've got these 2 points. And then we're also going to need the critical points. And so on my paper, I'm going to copy down the values I can see in the table. But I'm also going to need the critical points. So I'm going to write down h prime equals 0, and then I'm going to kind of report these x values right here. And there we go. And if I do the same thing I did before, where I like kind of cut off the y coordinate and just rename these a and b, I can actually type in a, b, and 7. Okay, now I wouldn't necessarily recommend doing that on your sheet of paper, but once you fill in your table with all your values of your critical points and your endpoints, you might check back in with a question and ask yourself for a second time, what's it asking for? It's asking for the minimum value of h, so that's going to be that negative 6.7. I'm going to emphasize that as my answer, and there will be good. Number two, don't use x or y as a function name. I mean lowercase x and lowercase y. And this is something that comes up quite a bit in AP Calculus. We got, maybe an object's moving along the x-axis, like this example, and an object's position at time t is given by x of t is t log t. And so I'm just going to go over here and I'm going to graph this on Desmos, typing it in just like I see it. And immediately something looks off. Okay, this t log t, this should be a function, and this is not passing the vertical line test. Okay, all the way back to algebra 1. So this isn't, something's off here. Moreover, x of t can't be taking in negative t values because we'd be taking the log of a negative number. That's not possible. So like, what's going on here? And really what it's thinking is it's trying to graph x equals y log y. Okay, and so we don't like that. So what I would recommend doing is just using capital X, and then all of a sudden it's like, oh, okay, yeah, no, it's capital X is the output variable and T is the input variable. Best I can understand, Desmos must think that lowercase x can only be an input variable. Now, lowercase y is a little bit trickier, but it doesn't really like y of t. It kind of might think that you're graphing an implicit relationship where it's like y times x equals that function of x on the right. So I really suggest avoiding that as well. Now, if I'm interested in whether this thing is heading toward or away from the origin at time t equals 0.5, I'm going to need to consider the position at time 0.5 and the velocity, so that would be x prime of 0.5. Okay, I'm going to report those values, and I might also sketch a diagram to help me make my decision, although just to remind you, a diagram or a graph for a sign chart is never going to be used as justification in AP Calculus on the free response section. But what really matters about this is the signs of these values. The fact that x is negative, but x is negative and x prime is positive. So I'm going to point that out, with a less than 0 and greater than 0, and then I'm going to conclude that the object is moving toward the origin. And my number one tip for Desmos on the AP Calculus exam is use it as much as you can. Do not be taking derivatives by hand or anti-derivatives by hand on the calculator section. It is just not going to be a time-efficient strategy, and oftentimes it's impossible with functions they give you. Okay, I really want you to use this as much as possible, but we need to be aware of some things. Okay, first of all, I don't want you to get bogged down in side quests. Desmos is cool. You can see some really cool graphs and you can explore, and it's really easy to waste time. Okay, so we need to be efficient, know what we're gonna do, get in, get out, take our results and be time efficient, because this is a time limited exam. And don't expect to use it on every multiple choice question that allows a calculator. There's the multiple choice calculator section, 15 questions, 45 minutes, but of those 15 questions, like less than half, oftentimes, about half, use a calculator, or the calculator is even helpful. So don't expect to use it on every problem, because again, you might end up wasting some time. What I do want you to do is round to 3 decimal places every time. It's always been like that. Just don't want you to forget, probably watching this, kind of some last second review, top tips. But yeah, round to 3 decimals. There's no sense in leaving any points on the table because we didn't round or possibly truncate to 3 decimals. It really doesn't matter, whatever you want to do. All right, so that's all I got for you for this video. Thanks for watching.